Hi, so this talk is about the graph homophily metric and how it relates to the performance of graph neural networks. So homophily is a measure of the tendency of similar nodes in the graph to connect to each other. So one particular instantiation in labeled graphs is label-dependent graph homophily, which is a fraction of all edges that connect two nodes with the same label. And empirical evidence until now suggests that graph neural networks, or GNNs, do not do too well on graphs with low homophily, otherwise known as heterophilic graphs, because a node in a vanilla GNN only aggregates information from its neighbors. And in a heterophilic graph, these neighbors could be quite different. So they could essentially be contributing noise to the center node instead of contributing useful information. So several long-range aggregation methods try to address this limitation of vanilla GNNs by allowing a node not only to aggregate information from its neighborhood, but also aggregate information from distant nodes in the graph. And these methods claim improved performance when solving node classification tasks on heterophilic graphs. However, with careful hyperparameter tuning, we can show that vanilla GNNs and even simple multilayer perceptrons that don't take the graph structure into account can outperform many recently proposed long-range aggregation methods. So there's obviously a problem with the common wisdom that GNNs do badly on heterophilic graphs, and that we need to augment them with long-range aggregation techniques in order to rescue the performance, because this is simply not the case. GNNs on many heterophilic graphs, vanilla GNNs, often outperform methods based on long-range aggregation. So we think one problem is a graph homophily metric itself, which is not a good predictor of GNN performance. So we propose another graph metric, the neighborhood information content metric. So the derivation of the metric starts by looking at the mutual information between the label of a node, L of V, and the label configuration of its neighborhood, L neighborhood of V. So L neighborhood of V is a set that can have a variable size, and it's simply the set of the labels of nodes that are neighboring to node V. So this mutual information is a direct measure of how much a vanilla GNN layer can reduce the uncertainty of its label prediction by observing the labels of neighboring nodes. So a general closed-form expression for this mutual information was not possible, so we derive a lower bound under the assumption that the probability that two nodes connect to each other only depends on their labels. So this lower bound is the neighborhood information content metric. So the expression looks quite daunting, but it's actually quite simple to evaluate for an arbitrary graph. So P sub S is the probability that a randomly selected node would have label S, while Q sub S of D is the probability that a node with label S would have degree D. Capital C is the number of labels, while capital D is the maximum node degree in the graph. C sub SR is the probability that a node with label S would connect to a node with label R. So we measure the performance of GNNs on several synthetic node classification graphs as we vary the homophily level. And if homophily were a good predictor of the performance of vanilla GNNs, we would have seen a monotonic relation in the graphs. But this is never the case. Almost all the graphs have a U-shaped behavior, where in some parts of the graph, if you actually decrease homophily, you get improved performance for the GNN. In this case, we're looking at plain GCN, graph convolutional network, as well as the graph sage networks. Both of them are GNNs that aggregate information from the local neighborhood. On the second y-axis, we plot the NIC, the neighborhood information content metric, and we can show that it correlates much better with GNN performance than homophily. So in summary, label-dependent graph homophily is poor predictor of GNN performance. And we show in several heterophilic graphs that as you actually increase or decrease the homophily level, the GNN performance would improve. And we have also shown that vanilla GNNs actually outperform recent methods based on long-range aggregation on several heterophilic graphs. And we've also introduced the neighborhood information content metric, which is an easy-to-evaluate metric that's a much better predictor of GNN performance on node classification tasks than graph homophily. And also NIC is theoretically grounded. It gives you a tangible quantity, which is a reduction of uncertainty when trying to predict the label of a node, the reduction of uncertainty by observing the labels of the neighboring nodes. And for more information, you can check our paper on arXiv, also called On Local Aggregation in Heterophilic Graphs. And thank you for listening.